入ってるか。OK そうですね。それでは始めます。3月1日の13時からっていうことなんだけど、まだ早いですけれども、追いかけ再生して、コーヒーこぼした。追いかけ再生していただけると思うので、入ってるか。ちょっとOK。はい、追いかけ再生いただけると思うので始めたいと思います。今日は255ページから255ページということで、このブルーキャットのページにあります。説明はテキストはここにあります。それで、どこかというとここで、ここにあります。これでいいのかな。それで開く。それで一応最初と最後言っとこうかな。ここのなんか行ってきてからよしとこのサスキンド QM っていうハッシュタグをつけることにしたので、ツイッターを使っている人はこのハッシュタグ言ってください。で、そうすると何を言おうとしたんだっけね。ブルーキャットいけます。そうその前にこうハッシュタグで、ここに行ってもらえると、こういうふうに次の希望の次回ね、次回どの枠だったら参加できますかっていうことが、こういうふうに、ツイッターで回答できるようになってますので、回答してください。ちょっと明後日以降は、こういう感じになってます。ちょっと夜しか時間が取れないので、夜の時間帯の中から選んでください。ツイッターやってない人は、YouTube の、にコメント残していただいてもいいし、ブルーキャットの方にコメント残していただいてもいいし、コンパスの方にコメント残しておいていただいてもいいです。何らかの形で私に連絡が来るようになれば、情報が伝われば、その時間帯に開催します。いいかな。それで255ページから255ページからです。Momentum and its eigenvectors っていうことです。Position is intuitive. Momentum is less intuitive. なんでだろうな。Position is intuitive. 直感的である。Momentum is less so. 運動量はそんなに直感的でない。Particularly in quantum mechanics. It will only be later that we see the connection between the operator that we identify with momentum and the familiar classical concept of mass times velocity. 運動量が mv であるっていうことは、後でやりますと。But I assure you that we will make the connection. このP イコール MV ということにつながるっていうことは、絶対にやるよと約束するよということです。For now, let's take the abstract mathematical route. The momentum operator in quantum mechanics is called P, and it is defined in terms of operator minus ID. D はディファレンシャルオペレーター。単なる、DDX っていう、微分演算子にマイナス i がついたのが運動量オペレーターですよと。 なんでこれが MV になるかっていうのは後でやるから、今は気にしないでいてくださいと。ちょっと、無茶ぶりっていう感じはするんだけど、これが、P です。As we saw earlier in equation 810, we need a factor minus I to make this operator Hermitian。ハミシアンは日本語ではエルミートって言われているやつですね。We could just define P to be minus ID, but if we did, we would run into a problem later when we connect these ideas to those of classical physics. The reason should be clear. There is a dimensional mismatch. In classical physics, the unit of momentum are mass times velocity. In other words, mass times length divided by time, ml over t. On the other hand, the operator d has unit of inverse length, or 1 over L. The resolution of the mismatch is provided by Planck's constant h bar, which has units of ml square divided by t. The correct relation between P and D is therefore P equal minus IH bar D, or in terms of its action on wave functions, P psi x equal minus IH bar D psi x dx。 いいのかな。Quantum physicists often use units in which h bar is exactly 1, and in that way simplify the equations. As tempting as it is, we won't do that here. Let's work out the eigenvectors and eigenvalues of P. The eigenequation in abstract vector notation is P equal P psi equal P psi. So this is operator. This is operator. This is eigenvalues. Where symbol P is eigenvalue of P. Equation 816 can also be expressed in terms of wave functions using the identification P equal minus IH bar ddx. We can write the eigenequation as これね、この P っていうのはこの部分。This is P. So this is P. P psi. This is capital P. P psi x equal small p psi x. So we can move this h bar minus IH bar to the right hand side, and you obtain this. Is this strange? I think it's okay. It's okay. So this is the type of equation that we've run into before. Differential equation. The solution has the form of an exponential. So this is the solution. So this one, if you put this here, you see this is the solution. So the subscript P is just a reminder that psi P is the eigenvector of P, with the specific eigenvalue p. It is a function of x, but it is labeled by an eigenvalue of p. どうしようか。The constant a multiplying the exponential is not determined by the eigenvector equation. That's nothing new. The eigenvalue equation never tells us the overall normalization of the wave function. As a rule, we fix the constant by requiring the wave function to be normalized to unit probability. An example that goes all the way back to section 2.3 is the eigenvector of the x component of spin. Okay, so this is the x component. How do we write? Anyway, so this is in this way. 1 square root 1 over square root 2. So 例えば sigma x r, this is plus 1 r. Excuse me. The factor 1 over square root 2 is there to make sure the total probability is 1. Normalizing the eigenvectors of P is a more subtle operation, but the result is simple. The factor A is only slightly more complicated than in the spin case. To save time, I will tell you the answer and leave it for you to prove later. The correct factor is A equal 1 over square root 2 pi. Thus, psi px equal 1 over square root 2 pi times exponential ipx divided by h bar. A point of some interest follows from equation 8.13 and 8.17. The inner product of a position eigenvector and momentum eigenvector has a simple and symmetric form. xp xp is this. Bracket xp is 1 over square root 2 pi times exponential ipx divided by h bar. Bracket px is 1 over square root 2 pi times exponential minus here's minus ipx divided by h bar. So the second equation is simply the complex conjugate of the first. These results are easy to verify if you keep in mind that ket x is represented by a delta function. I'd like to mention two important points before moving further. I think this part, don't worry, a little bit difficult, so don't worry. It's a little bit difficult to follow, so let's do more two important points. Number 1, equation H17 represents a momentum eigenfunction in the position basis. In other words, although it represents a momentum eigenstate, it is a function of x, not an explicit function of p. Number 2, we've been using the symbol psi for both position and momentum eigenstates. A mathematician might not approve of using the same symbol for two different functions, but physicists do it all the time. Psi x is just a generic symbol for whatever function we happen to be discussing. We've been using a symbol psi for both position and momentum eigenstates. そうだっけ? Psi. Anyway. Mathematicians might not approve of using the same symbol for two different functions, but physicists do it all the time. Psi x is just a generic symbol for whatever function we happen to be discussing. This is generic function. Anyway, okay. At this juncture, we begin to get a glimmer of why the wave function is called the wave function. What you should notice is that the eigenfunctions, wave functions representing eigenvectors of the momentum operator, have the form of waves, sine waves and cosine waves to be precise. In fact, we can now see one of the most fundamental aspects of the wave-particle duality of quantum mechanics. Sorry, I think I forgot to announce the site. Let me see. I forgot to announce this link to the. Let me do it now. Compass. こうだ。よしと。I hope this is okay. それでブルーキャット。I have to do this. How can I? ここか。こことこことこれ OK か。OK. I hope this works. Okay. What should いいかいか。これはそっかさ。What you should notice is that the eigenfunctions, wave function representing eigenvectors of the momentum operator have the form of waves, sine waves and cosine waves to be precise. In fact, we can now see one of the most fundamental aspects of the wave particle duality of quantum mechanics, the wavelength of the function exponential IPX divided by h is given by wavelength of this is given by lambda equal 2 pi h bar divided by p, because the value. So I think easier way is you can just do 2 pi divided by k, or even easier than this is k equal 2 pi divided by lambda. This is the easiest definition to remember, because the value of the function is unchanged. If we add 2 pi h bar divided by p to the variable x, so here this is lambda, yeah. So let's pause for a moment to discuss the importance of this connection between momentum and wavelength. It's not just important in many ways. It is the relationship that defined 20th century's physics. Over the last 100 years, physicists have primarily been concerned with uncovering the laws of the microscopic world. This has meant figuring out how objects are built out of smaller objects. The examples are obvious. Molecules are made from atoms, atoms from electrons and nuclei, nuclei from protons and neutrons. These subnuclear particles are constructed out of quarks and gluons, and the game goes on as scientists search for even smaller and more hidden entities. All of these objects are too small to see with the best optical microscopes. All of these objects are too small to see with the best optical microscopes, let alone the naked eye. The reason is not just that our eyes are insufficiently sensitive. The more important fact is that eyes and optical microscopes are sensitive to the visible spectrum, which comprises wavelengths at least a few thousand times longer than the size of an atom. As a rule, you can't resolve objects much smaller than the wavelengths you are using to look at them. For this reason, the story of 20th century physics was in large part a quest for smaller and smaller wavelengths of light, or any other kind of wave. In Lecture 10, we will discover that light of a given wavelength is composed of photons. In Lecture 10, we will discover that light of a given wavelength is composed of photons whose momentum is related to the wavelength by exactly the relation. Same relation. This is same relation. 2 pi over k or k equal 2 pi over lambda. The implication is that to probe objects of ever smaller size, one needs photons or other objects of even larger momentum. Large momentum inevitably means large energy. It's for that reason that the discovery of the microscopic properties of matter required increasingly powerful particle accelerators. Okay, so we move on to next section. Section 8.3, Fourier transforms and the momentum basis. Fourier transforms and momentum basis. The wave function psi x has the important role of determining the probability for finding the particle at position x. Or this is probability density. I think this probability density is like this. As we will see, no experiment can determine both the position and momentum of a particle simultaneously. But if we forego determining anything about the position, momentum can be measured precisely. forego は何でしょう。forego見捨てる、無視する、見捨てる、forego見捨てる。If we forego determining anything about the position, momentum can be measured precisely. The situation is quite analogous to that of the x and z component of a spin. Either value can be measured, but not both. What is the probability that a particle has momentum p if we choose to measure it? The answer is a straightforward generalization of the principles laid down in Lecture 3. The probability that a momentum measurement will give momentum p this is a strange. これは違うです。これはスモーp. So I think this has to be a small p. pp probability density of p is the entity p psi is called the wave function of psi in the momentum representation. Naturally, it is a function of p and is denoted by new symbol. I don't know. He said he doesn't use different symbol here. number 2. He said this is the generic symbol for whatever function we happen to be discussing. Anyway, so he used 2 symbols finally. This is momentum. So this one symbol, second symbol, and there is a tilde, psi tilde p. Anyway, entity bracket p psi is called a wave function of psi in the momentum representation. Naturally, it is a function of p and is denoted by a new symbol. So sorry, confusing. Sorry for the confusion. This one. And I think this has to be small p. It is now clear that there are 2 ways of represent a state vector. One way is in the position basis and the other is the momentum basis. Both wave functions, the position wave functions psi x and the momentum wave function psi tilde p, represent exactly the same state vector ket psi. It follows that there must be some transformation between them, such that if you know psi x, the transformation produces psi tilde p, and vice versa. In fact, the 2 representations are Fourier transform of each other. はい、行きましょう。Next one is 8.3.1 Resolving the Identity. We are about to see the great power of the Dirac bracket notation in simplifying complicated things. First, let's recall an important idea from earlier lectures. Suppose we define an orthonormal basis of states through the eigenvectors of some Hermitian observable. Call the basis vector I. In lecture 7, I explained a very useful trick, and now we are going to see just how useful it is. It is called resolving the identity. The trick given in equation 7.11 is to write the identity operator I, the operator that acts on any vector to give the same vector, in the form so this is any basis. This can be I, can be any basis vector. Then this is very important. This is very important. Okay, let me go back a little bit. Resolving the identity. Resolving the identity. We are about to see how great power of the Dirac bracket notation in simplifying complicated things. First, let's recall an important idea from earlier lectures. Suppose we define an orthonormal basis of states through eigenvectors of some Hermitian operators. So this is eigenvectors of some Hermitian observable. So this is a basis. This provides a basis set. This provides a basis set, and this basis vector I can be any basis vector. That means any eigenvectors of any Hermitian observable. Anyway, then you put I in this order. Ket blah, this order. Then you take summation over I, O index. And that, so this is more like this. This thing is identity operator. So this is important, important equation to remember. Because momentum and position are both Hermitian, the sets of vectors xk and set of vectors pk each define basis vectors. By replacing summation with integration, we discover two ways to resolve the identity. So this both 821 and 822 are identity operators, xx or pp. Then sum over x or sum over p, summation over x or summation over p, and this summation is replaced with integral. So there is an integral with respect to dx, with respect to x, and integral with respect to p. Let's suppose that we know the wave function of the abstract vector. We know the wave function of the abstract vector psi in the position representation. By definition, it is equal to this. This is the wave function in position representation. Now suppose we want to know the wave function psi tilde p in the momentum representation. Here are the steps laid out in detail. First, use the definition of the momentum representation wave function. Use the definition of the momentum representation wave function. Psi p tilde is p bracket p psi. Now, insert the unit operator. So this is the unit operator. Sure. This is equal I. So we insert this unit operator here. We insert the unit operator between bra and ket vectors in the form given in equation 8.21. So we obtain something like this. The expression bracket x psi is just a wave function psi x, and bracket px is given to us by the second equation of equation 18. So this is just like okay. So this is an exponential part here. So this thing is psi x, and the other these things is this thing. Putting it all together, we find that so psi tilde p is 1 over square root 2 pi integration with respect to x times exponential minus ipx divided by h bar times psi x. This equation shows us exactly how to transform a given wave function in the position representation into the corresponding wave function in the momentum representation. What is it good for? Suppose the position wave function for some particle is known. However, the goal of your experiment is to measure the momentum, and you want to know the probability of observing momentum p. The procedure is to first calculate psi tilde p by using equation 824 and then compute the probability. P probability density psi star tilde p psi tilde p. It's just as easy to go the other way. Suppose we know psi tilde p and wish to recover psi x. This time we use equation 822 to resolve the identity. Here are the steps. Notice that they look suspiciously similar to the earlier ones. First, use the definition of the position representation wave function. This is what we want to know, I think. Yeah. This is what we want to obtain. Now insert the unit operator between the bra and ket vectors in the form given in equation 822. So this is the identity operator, this part and this part. So we inserted this one to here. So then the expression p psi is just a wave function p tilde p, psi tilde p, and bracket pxp is given to us by equation 818, but this time it's the first of the two equations. So here in this case, no, here no minus. Yeah. So then putting it all together, we find that psi x equal 1 over square root 2 pi integration with respect to p exponential IPX divided by h bar times psi tilde p. This is the psi x. Let's take another look at the two equations for going back. Let's take another look at the two equations for going back and forth from position to momentum. Notice how symmetrical they are. The only asymmetry is that one equation contains exponential IPX divided by h bar and the other contains exponential minus IPX divided by h bar. Very symmetric. Only asymmetry is here. Anyway, the relation between the position is this strange? Anyway, this look a little bit strange. Okay, to me, if this is a K, it's okay. If this is a K, then this is a K. Can we make this K, K, K? This is completely okay. But if we change K to P, yeah, so this is more like, how to say, how you say, this is P divided by h bar, and this is okay, P divided by h bar, yeah. So this is okay. So then this K, dk, this is like h bar 1 over h bar divided by dp. This is okay. This is p divided by h bar. Then this part, p divided by h bar. So the question is this: there may need h bar. Maybe this is square root. This has to be square root 2 pi h bar. Anyway, We will see later. The relation between position and momentum representation summarized by equation 825 is that they are reciprocal Fourier transforms of one another. In fact, these are the central equation in the field of Fourier analysis. Central equation in the field of Fourier analysis. I want you to notice how easy it was to derive those equations using Dirac elegant notation. Okay, so we stop. I stop here. 265 here. Let's see. 編集 Next time is 265. Then I want you to check. See, want you to answer. Okay, today, but 1st of March, I can continue from 2 o'clock, but this is already finished. So I can do from 4 o'clock too today. So please hit this. Then March 3, we can do 9 o'clock in the evening. Okay, so see you next time. I will update the information.